Thank you for being part of Dr. Emmanuel's Engineering Mathematics class, lesson number 12. We're covering applications of eigenvalues. We've been looking so far at eigenvalues and eigenvectors. We've been looking at perpendicular lines, orthogonal. We're finding here we can transform in different ways. So we're going to be transforming to information that shifts points according to their distance from perpendicular axes. So we're going to be looking at, we have a U axis here and we have a V axis. And we can tell that these are what? Perpendicular to each other. We like to change from X and Y to X prime and Y prime. And so this is the two equations, and this is it in matrix form. Okay, as you can tell here, you have a diagonal of 1, and the only values that are going in is the kx and the ky. Two eigenvalues and eigenvectors describe the directions, magnitude of this shear. Okay? Our first example. Find the eigenvalues and eigenvectors for a shear described by kx equals 2 and ky equals 8. Okay, as we see here, we can see the two vectors here perpendicular, u and v. We're now substituting. We're using still the diagonal as 1, and we're only substituting for kx and ky. Okay, so now all we have to do is plug in our eigenvalues, our lambda to represent our eigenvalues. And so it'll be a minus lambda I. So it'll be 1 minus lambda on the diagonal and 1 minus lambda on the diagonal. When we multiply this together, we get 1 minus lambda squared minus 2 times 8, which is 16. So then we have lambda squared minus 2 lambda minus 15. 16 minus 1. And now we have lambda. Our eigenvalues are 5 and minus 3. So the next step is to plug in our eigenvalues into our equation. And let's see what we get here. So if we plug in 5, where we have lambda, it's 1 minus 5, 1 minus 5. That gives us a minus 4 on the diagonals. And so when we do our cross multiplication, or when we look specifically here at this equation, this will be a minus 4x plus 2y equals 0. So what we would like to do is be able to convert this over, and we see that if we bring the 4x to the other side of the equation, we get 2y equals 4x, which implies that y is equal to 2x. Okay, so that means that if we plug in for x equal 1, then y equals 2. And we have the components 1 and 2. So next, that's our eigenvector. We found our first eigenvector. So now we're looking at our eigenvalue of a -3, and we're plugging it in. So this is 1 minus lambda, which is a -3, turns into a +3. We multiply these together. We add these together, and we see that we get a 4 coming down our diagonals. And so now we have 4x plus 2y equals 0. And if we take the 2y and put it on the other side of the equation, we get minus 2y equals 4x, which implies that you divide by 2, that a minus y equals 2x. And so now we've found, if we plug in for x equal 1, then we can see that y equals a -2. So now we have our second eigenvector. And what does it look like? Okay, here we have our first eigenvector, which is 1 and up 2. And then we find our second eigenvector, which is 1 and -2. Now what we would like for you to do is be able to practice this. Okay, so please find the eigenvalues and eigenvectors for the share described by kx equals 4 and ky equals 1. You should have no problem with this. At this time, we're going to take our first break, and we're going to come back and look at applications for RLC circuits.